Good morning, everyone. Today is my pleasure to introduce Shengtong Zhang from Stanford University, and he's going to talk about squares of eigenvalues and semi-definite optimization. Okay, so take it away.
And okay, thanks for the introduction, Thomas. Yeah. So today I'm going to talk about some problems related to squares of eigenvalues. I think Elphick covered one of those problems, and since then I have made some progress. Yeah, so I plan to talk about two conjectures today. One is a very nice conjecture by Elphick-Farber-Goldberg-Wocjan. I think Professor Elphick talked about the conjecture in his talk about a few months ago. And the second is called the Bollobás-Nikiforov conjecture. I will first introduce these two conjectures and state what I proved, and then I will give an overview of my proof method that works. Okay. So let us start with the Elphick-Farber-Goldberg-Wocjan conjecture, which I'll sometimes abbreviate by EFGW, the initials. So this is a conjecture about the graph spectrum. So let us fix some notations. So G is always a simple graph with n vertices and m edges. So let AG be the adjacency matrix, and let lambda i's be the eigenvalues of the adjacency matrix. So these are what we call the graph spectrum, and since AG is symmetric, these are all real numbers. By convention, we sort them in decreasing order. So lambda 1 is the largest. We also call the spectral radius. And lambda 2 is the second largest, sometimes called the second eigenvalue, and so on. Let Vi be the normalized eigenvectors correspond to lambda 1 and so on. Well, we won't be using this for quite a while. And finally, we use n plus, n0, n minus to denote the inertia of the adjacency matrix. This is just how many positive, 0, and negative eigenvalues does AG have. Okay. So these quantities are all functions of G, but for this talk, I plan to hide the dependence on G when there's no ambiguity. So the EFGW conjecture is something called the square energy. It's about something called the square energy. Let me start by recapping what the graph energy is. So the energy is defined as the sum of the absolute values of all the eigenvalues. And one property of the energy is that since the adjacency matrix has 0 trace, the sum of the eigenvalues is 0. So we can write the energy as twice the sum over all the positive eigenvalues, and also as twice the sum over the negative eigenvalues, just with a sign flip. Okay. So the energy, I think, is quite famous in the spectral graph theory community. So it was introduced by chemists to study molecules in the 1960s. It has since then been extensively studied. I mean, I'm sorry I couldn't list all the literature on energy, but I think a recent very cool application is that Ratti, Thomás, and Sudakov used graph energy to prove like highly non-trivial results related to discrepancy theory. So but I won't be directly working with energy today. I'll work with something called square energy. So the square energy is an L squared analog of energy. And the idea is that in this definition, we can replace lambda I with lambda I squared. Well, why don't we replace lambda I with lambda I squared in this definition is because the sum of the eigenvalues squared is just twice the number of edges. So it is so there's nothing much to say about the sum of eigenvalues squared. Instead, we can study we can like separate the positive and negative eigenvalues like this and define the positive square energy as the sum of squares of all the positive eigenvalues and the negative square energy as the sum of squares of the negative eigenvalues. These add up to 2m, but individually, I think they're quite interesting quantities. And here's an example. So for the complete graph, its spectrum is 1 times n minus 1 plus n minus 1 times minus 1, right? So its positive square energy is n minus 1 squared, and its negative square energy is n minus 1. Another example is bipartite graphs. So for bipartite graphs, the spectrum is symmetric. Therefore, the positive eigenvalues and the negative eigenvalues are the same. They are both equal to m. Okay. So any questions so far? Okay, so here are some motivations for studying square energy. First of all, I think it is a pretty natural analog. It's a pretty natural analog of energy, and it is actually related to energy by the Cauchy-Schwarz inequality. And second, I think this is the original motivation of why the energy was introduced, is that it gives a lower bound for the chromatic number. So this is work by Elphick-Wocjan in 2013. And I think this is a conjecture in their paper. And this conjecture was resolved by Endo Lin in 2015. So this lower bound states that the chromatic number is lower bounded by 1 plus S plus over S minus, and same for S minus over S plus. Yeah. So this result will also play a role in what I will talk about, and it has recently been proved first by Gore and Spier and by Coutinho and Spier. Yeah. And finally, it is also featured in the work I mentioned on discrepancy theory by Rati, Thomás, and Sudakov. In fact, they use both energy and square energy, and they analyze the relation between them. And I don't think the word square energy actually appear in their paper because because they might not know that the quantity they study have this name, but yeah, it definitely appeared implicitly. Okay, so having defined the square energy, let us look at the first conjecture we will study today, which is the Elphick-Farber-Goldberg-Wocjan conjecture. So this conjecture asks a very natural question, which is, what is the extremal value of the square energies over connected n-vertex graphs? Well, their conjecture is that if G is a connected n-vertex graph, then the minimum of S plus and S minus is at least n minus 1. In other words, both S plus and S minus are always at least n minus 1. Equivalently, since the sum of S plus and S minus is equal to 2 times the number of edges, this is the same as saying that the maximum of S plus and S minus is at most 2m minus n plus 1. And here's a quote by Elphick from his talk. So apparently Professor Elphick is pretty happy about this conjecture, and he regarded it as his best conjecture to date. Okay. So why is this conjecture interesting? Well, first of all, it is a significant strengthening of a spectral radius bound by Hong proposed in 1988. So Hong proved that the first eigenvalue squared is at most 2n minus n plus 1. And this conjecture is saying that not only is the first eigenvalue squared at most this quantity, but if you square all the positive eigenvalues and add them together, it is also at most 2n minus n plus 1. In addition, this conjecture has a pretty curious equality condition. So it is tight when G is any tree, because as we said, bipartite graphs has S plus and S minus equal to M. Any tree is bipartite and have n minus 1 edges. So for any tree, S plus and S minus are both equal to n minus 1. In addition, well, the negative square energy can also be equal to this lower bound when G is a complete graph. So it is tied at the two extrema of connected n-vertex graphs. It is tied for like the sparsest possible graph, and it is also tied for the densest possible graph. Yeah. So this makes this conjecture quite interesting given this curious equality condition. Okay. So there has been a number of studies on this conjecture before my work. So first of all, Elphick-Farber-Goldberg-Wocjan proposed this conjecture in their 2016 paper. And in that paper, they proved the conjecture for regular graphs, bipartite graphs, and dense random graphs. So I think the regular graph proof is the most remarkable one because it involves the chromatic number bound for square energy in a pretty interesting way. Later in 2023, Abia, De Lima, Desai, for Ogben and Madrid, they further proved the conjecture for several graph families, and they also provided valuable computation evidence for the conjecture. And finally, in 2023, Elphick and Wocjan revisited the conjecture in another paper, and they said that it might be too hard to prove, so they proposed a weaker conjecture, which is the minimum of, which is both the positive and negative square energy is at least the maximum of the positive inertia and the negative inertia of the graph. So recall that the conjecture says it is at least n minus 1. This relaxes it to n plus and n minus, both of which are at most n minus 1. So this weak conjecture has a pretty interesting interpretation. It is saying that the mean square of the positive eigenvalues is at least 1, and it's the same for the negative eigenvalues. Well, this is because S plus is the sum of squares of the n plus positive eigenvalues. So having summarized like past works, and let me present my first main theorem on the EFGW conjecture. And so to state my main result, I need one more concept. So a dominating set is a set of vertices such that every vertex is either in the set or is a neighborhood of some vertex in the set. The domination number is the minimum size of a dominating set. And I proved in a paper that's on arXiv right now that if G is a connected n-vertex graph, then the minimum of the positive energy and the negative energy is at least n minus gamma. Of course, this is not a full conjecture, but it has several implications for the conjecture. Here are some corollaries. So I think the corollary I'm most happy about is that this theorem verifies the EFGW conjecture when the graph has a dominating vertex, also called a universal vertex. This corresponds to the case gamma equal to 1, and when gamma equal to 1, this right-hand side is precisely what EFGW predicted. Furthermore, it implies a general linear lower bound for S plus and S minus. So there's a full lower bound for the domination number, gamma at most n over 2. And so this result shows that for any connected n-vertex graph, S plus and S minus is at least n over 2. Well, you have to rule out the trivial case n equal to 1, but when n greater than equal to 2, this does hold. So I think this is the first linear lower bound. Previously, the best lower bound is of the form square root n for general graphs. And actually, Akbari, Kumar, Mohar, and Pragada also obtained this linear lower bound simultaneously, and their lower bound is slightly stronger, which is 3n over 4. Yeah. And finally, using some other like upper bounds for the domination number, I can verify the weaker conjecture of Elphick and Wocjan proposed proposed last year. So I can show that both S plus and S minus is at least the maximum of n plus and n minus. Yeah. So this is my result on the EFGW conjecture. So any questions? So if not, let us move on. Okay, if not, let me talk about another conjecture. So this is the Bollobás-Nikiforov conjecture. So Bollobás-Nikiforov conjecture comes from torrent theory, which is another important area of extremal combinatorics. So, so I'm going to use omega to denote the clique number of G. Torrent theorem, which is the foundational theorem of extremal graph theory, says that for any graph G, we have the number of edges is bounded above by n and omega. So more precisely, the number of edges is the most n squared over 2 minus n squared over 2 omega. So I might have written it in a slightly unusual way, this right-hand side. But here's how I interpret this theorem. So this n squared over 2 here is a sort of trivial upper bound for number of edges. That's valid for all graphs, right? Now this n squared over 2 omega is an improvement factor that you can gain under the assumption that G forbids a small clique. So this is a trivial bound, and this is an improvement factor. Later, people realized that torrent theorem can be phrased as a statement involving the spectral radius of a graph. Wilf proved in 1986 that the following so-called spectral version of torrent theorem. So it says that the spectral radius of a graph is the most n minus n over the clique number. Again, this n here is the main term, is a trivial upper bound, and this n over omega is an improvement factor. Nikiforov in 2002 further proved that the square of the first eigenvalue is the most 2m minus 2m over the clique number. So again, this 2m is an upper bound for lambda 1 squared, and this 2m over omega is an improvement factor. And the relation between these three theorems is that by the Rayleigh bound lambda 1 greater than or equal to 2m over n, Nikiforov theorem is actually the strongest, and it implies both Wilf's theorem and Torrent's theorem. In addition, Wilf's theorem also implies Torrent's theorem. So this leads us to the Bollobás-Nikiforov conjecture. And if you look at these two spectral versions, they only involve the spectral radius. And Bollobás-Nikiforov brings the second eigenvalue into the mix. So the second eigenvalue is an important quantity in my opinion. It is related to the expansion property of the graph, and this is the reason why I like this conjecture, is that it also plays a role in the theory of equiangular lines, which is something I worked on before. Okay. So the conjecture is that in this spectral torrent theorem of Nikiforov, you can insert the second eigenvalue onto the left-hand side. And the theorem will still hold, except you have to rule out the complete graph. And this is a technicality to prevent lambda 2 from being negative. Well, since all the eigenvalues squared is is equal to 2m, this 2m is still a trivial upper bound to lambda 1 squared plus lambda 2 squared. And this conjecture is again stating that we can save 2m over omega over this trivial bound. Okay. So I think these two conjectures actually share a lot of similarities, even though I don't think their proof methods are particularly like I don't think they are like equivalent to each other or like very similar to each other, but they do share a lot of interesting similarities. So I think one similarity is that they both involve the squares of eigenvalues. And the other similarity is that they have very strange equality condition. So the usual Torrent theorem and Nikiforov theorem, they are okay. So Torrent theorem is tight if and only if G is a balanced Torrent graph, and Nikiforov theorem, Nikiforov spectral Torrent theorem is tight when G is a balanced Torrent graph plus isolated vertices, and when the clique number is at least 3. So when the clique number is equal to 2, it turns out complete bipartite graphs are also tight example. However, the Bollobás-Nikiforov conjecture, it has a number of other tight cases known. So it is tight for balanced Turing graphs, as in Turing's theorem. It's also tight for the disjoint union of two balanced Turing graphs. And finally, this is observed rather recently, but it is also tight for blow-ups of the 4 paths and the 5 paths. So I think the 4 paths is just a complete bipartite graph, so it's perhaps not interesting, but the 5 paths, it is not a complete bipartite graph. It is therefore not a Turing graph at all. So, but it somehow also makes this inequality tight. This probably shows that the conjecture is non-trivial and interesting. And people have been trying to verify this conjecture for special cases. So I think the first work is that Endo Lin verified this conjecture in 2015 for the weakly perfect graphs. So a graph is weakly perfect if its chromatic number is equal to its clique number. Then there wasn't progress for many years, but in 2021, in another breakthrough, Lin and Wu managed to verify the conjecture for all triangle free graphs, which corresponds to the case when the clique number is equal to 2. And in the process, they also discovered this P5 tight example. Later, I myself verified the conjecture for all regular graphs, and Kumar and Pragada verified the conjecture for triangle sparse graphs, which are graphs with like few triangles. Yeah, and yeah, I think this is about the this is pretty much the extent of our knowledge for this conjecture right now. And well, for special graph families. So what if we study general graph? So we study general graph and we aim for a weaker upper bound because we cannot solve the conjecture completely. So before our work, I think there has been a sequence of works. Okay, so Endo Lin's work is so this is the same as the 2015. I think I just made a typo. But so starting from Endo and Lin, and so starting from Endo and Lin, And there's this general upper bound on lambda 1 squared plus lambda 2 squared. Well, their bound is sort of, you first upper bound it by the positive square energy, and then you use this chromatic number bound that I mentioned before. So and when Ling proves like 2m minus 2m over the chromatic number, and Spier replace the chromatic number with a fractional chromatic number, and Coutinho and Spier replace the fractional chromatic number with the so-called vector chromatic number. Well, this is probably not a very familiar notion to many people, but I think just know that it is upper bounded by the fractional chromatic number and the chromatic number, and it is lower bounded by the clique number. So this is still weaker than this. Okay. So this works well in many situations. In particular, if the chromatic number is equal to the clique number, then this is just the full conjecture. And that's how they did it for weakly perfect graphs. But for general graphs, like these two upper bounds can be quite far apart in terms of the saving factor. So Bala showed that there are graphs with bounded clique number but polynomially large vector chromatic number. So for these kind of graphs, this saving factor is going to be polynomially smaller than this saving factor. Yeah. So in other words, if we want to write this bound entirely in terms of m and omega, it's going to be pretty far away from this bound. Yeah. Okay. So in a recent paper, Coutinho, Spier, and I bridged this shortcoming, and we managed to prove that when G is not complete, lambda 1 squared plus lambda 2 squared is the most 2m minus 2m over 1.43 omega. So this is within a constant factor of this. In addition, we managed to prove a tighter bound for large clique number. So we proved that lambda 1 squared plus lambda 2 squared is the most 2m minus 2m over this omega plus a lower order factor. So when the clique number is large, this bound is within 1 plus small of 1 of this factor. So any questions about this? Okay. If not, let me put a disclaimer. So I don't have a so while that I think this is a progress towards this conjecture, I don't have a solution to the full conjecture yet. So as far as I know, like I have thought about these two conjectures for a while, and I think they are still wide open right now. So I don't think I think there's still some crucial idea that's missing that's preventing us from proving these conjecture. Yeah. Okay. Having stated my main result, let me briefly describe the proof method. Well, actually, let me use the remaining like 20 minutes to describe the proof method. Okay. So I'm going to talk about the EFGW conjecture in detail, and for the Bollobás-Nikiforov, I'm going to be a bit brief. Yeah. So this is the main theorem for the EFGW conjecture. It says that the graph energy, the square energies are lower bounded by n minus gamma. Gamma is a domination number. So the proof of this theorem can be divided into two steps. The first step is we prove I call super additivity property for the square energy. And this property says that if we partition the vertex set into two subsets, then the square energy of the whole graph, both positive and negative, is lower bounded by the sum of the corresponding square energy for the subgraph induced on V1 and the subgraph induced on V2. So this property it is simultaneously discovered by Akbari, Kumar, Mohar, and Prakada, and they use it to prove 3/4. Yeah. Yeah, so actually this property alone gives a linear lower bound, which is novel. Yeah. As an aside, this property also holds for the energy. So it's quite interesting that something could hold for both the energy and the square energy. Yeah. And after I prove this, I turn my attention to graphs with a universal dominating vertex. And I managed to prove the conjecture for all graphs with a universal and a dominating vertex. So in other words, for all such graphs, the positive and negative square energy are at least n-1. So this is the second step of the theorem, and together they imply the theorem via an easy argument. So in particular, we can partition G into gamma-induced subgraphs, and each with a universal vertex. So to do this, you like take a small dominating set, and for each vertex, you put it into the subgraph corresponding to the vertex in the dominating set that neighbors it. So yeah, if you have a dominating set here, right? Like every vertex is adjacent to one of them. So just partition the graph, like according to which vertex it is adjacent to. Yeah. So both of these steps involve what I call the semi-definite optimization method. And I will illustrate this method by giving a proof of step 1, this super additivity property. The key idea is, as I wrote here, to view S plus and S minus as semi-definite optimization problems. So because we're doing semi-definite optimization, here are a few standard notations. So I write M like curly greater than or equal to 0 if M is positive semi-definite, and this is the Frobenius norm. It is just you regard M as a vector and take its L squared norm. Yeah. So then the key lemma is that we can view S plus and S minus as the value of this semi-definite optimization problem. So S plus is minimizing over all positive semi-definite M, the Frobenius norm squared of AG plus M. And in other words, this is the square distance to the negative semi-definite cone, if you know what it is. So S minus is the same thing, except this plus is replaced by a minus. So it is, in other words, the distance to the positive semi-definite cone. And with this lemma, this super additive property is actually pretty easy. Because for any positive semi-definite matrix M, like this left-hand side is summing the square of all the entries of AG plus M, and this is only summing the entries in V1 with rows and columns corresponding to V1, and this is summing the entries with rows and columns corresponding to V2. So this right-hand side is summing over less entries than the left-hand side, so it is going to be so there's an inequality relation between them. And once you take the minimum over all positive semi-definite matrix and use this lemma, this immediately implies this. So with under the lens of semi-definite optimization, I think this theorem is actually pretty easy to see. Yeah. Okay. So it remains to prove the semi-definite characterization. This is like I proved this myself first, but later I read some textbooks on convex optimization, and it turns out that in the convex optimization literature, this is quite a folklore and basic result. But yeah, and in fact, I'm also inspired by Ando Lin's 2015-2016 work on this. Which I think is the first work that uses this result from convex optimization in spectral graph theory. Yeah. Okay. So for completeness, let me include a proof. We have the spectral decomposition. I mean, you can write the adjacency matrix as a sum over all the eigenvalues of like this VI transpose. So we can decompose the adjacency matrix into two positive semi-definite matrices, A plus and A minus, corresponding to the positive and the negative eigenvalues. So we have this decomposition, and it turns out that A plus and A minus are both positive semi-definite, and their Frobenius norms are precisely the positive and negative square energy. This is easy by looking at how they're defined. Okay, so therefore the upper bound of this program is straightforward. So by taking m equal to a minus, this becomes a plus. So its Frobenius norm squared is just the positive square energy. Similarly for this. Okay. So this shows that S plus G is greater than is at least a minimum. So I need to show that it's at most a minimum. In other words, I need to show that for any positive semi-definite matrix M, this is at least S plus G. This follows by expanding the Frobenius norm like this. And it turns out the crucial observation is that 1, AG plus and AG minus have zero inner product. And 2, AG, since M is positive semi-definite, the inner product between AG plus and M is non-negative. So therefore, like this whole term is non-negative. This is also non-negative. So therefore, like AG, we can bound them below by 0, and therefore AG plus M Frobenius norm squared is at least positive square energy. And the exact same reasoning holds for negative square energy. Yeah. Okay. So this concludes part 1 of the proof for EFGW. Part 2, I think, is not as straightforward as part 1 and involves some numerical coincidences. So let me just acknowledge that Abiyad, Abiyad and others in the 2023 work already proved the positive square energy part. Well, the positive square energy part is actually actually has a short proof, so it is just because the spectral radius of G is at least root n-1. So just taking the spectral radius is enough to prove the positive square energy part of this result. Unfortunately, this approach I don't think generalizes at all to the negative eigenvalue, because it is possible for the negative eigenvalue to be all -1. So you cannot like just prove the negative eigenvalue part of this using just a few eigenvalues. And instead, the key observation I had is to argue this by induction, and induction is made possible by this lemma, which I call the P3 deletion lemma. So it says that if G has an induced copy of P3, then we can remove some vertex in the P3 to decrease S minus by at least 1. So note the sum here. So there are 3 possible vertices, and I'm claiming that you can delete one of them. You can delete one of them. So as an example, here is a graph with negative square energy around 5.07. This is pretty close to the lower bound of 5 predicted by EFGW. And this is here, the red vertices is an induced copy of P3. Okay. Let us see what happens if we delete A. So if we delete A, the square energy goes down from 5.07 to 4.09, which is less than 1. Okay, this is bad since we cannot run the induction if this happens. And the same situation appears if we delete F instead of A. So the negative square energy is also the same. However, if we delete the vertex B, then the negative square energy drops down drastically to 2. So actually, in this copy of P3, the only deletion operation that works is deleting this vertex B. So that is why I stated remove some vertex here, because this does not hold if we just remove any vertex of the P3. We need to carefully choose which vertex we are removing. So I won't go into too much detail about the proof here. So it also uses a semi-definite characterization. And using this characterization, you can form a lower bound for the decrease in negative square energy. This lower bound involves a sum over all the vertices, which, to be frank, I think is very hard to analyze. I have been trying to analyze this for a while, but nothing worked. But for this particular case, it turns out that we can restrict this sum over all the vertices to just the 2 other vertices in P3. This, of course, loses a lot in general, but it is sufficient. And this lower bound is actually, after some very delicate operation, after some very precise calculation, this lower bound is actually barely greater than 1. So yeah, there's a numerical coincidence involved in this proof. In contrast to the proof of part 1. Okay. So once we have this P3 deletion, this theorem follows quite easily by induction. So we induct on N, if this G minus V star has any P3, we use this lemma to finish by induction hypothesis. Otherwise, G minus V star has no induced P3, so it is a disjoint union of cliques, and we can actually write down the spectrum quite explicitly and just verify this directly in this case. And so for Bollobás and Nikiforov, so for the Bollobás and Nikiforov conjecture, well, I think I finished sketching the entire proof of the EGFW conjecture here. So for the Bollobás and Nikiforov conjecture, well, it's quite it's somewhat similar, I would say, but the semi-definite program we use is different. So the reason we use a different semi-definite optimization problem dates back to Endolin's original work. So this is this is another optimization program for the positive square energy. And Endolin's main observation and Endolin's like one key trick is to apply the Cauchy-Schwarz inequality. And well, this is because like if you look at this program, right, it is not a very friendly optimization program, let's just say. It has this like AGM inner product squared. So I don't think it's an SDP in the usual sense. So to fix this, Endolin applied Cauchy-Schwarz and reduces the program to this program. And then the other crucial observation is this entry-wise product, also called the Schur product, is positive semi-definite. So this is called Schur theorem. So this is called Schur theorem that M entry-wise product with itself is positive semi-definite if M is positive semi-definite. Therefore, if we yeah, no, I'm running out of time. So therefore, like doing some rearrangement and using this property that AG minus chi minus 1 over chi is negative semi-definite, this gives us Endolin's theorem. So Coutinho and Spier, their 2023 work follows the same proof, but at the end, they use this semi-definite program characterization for the vector chromatic number. In our work, the crucial observation is that there's one more constraint we can put. So we can put this low rank constraint on this semi-definite program that Coutinho and Spier introduced. And this low rank condition allows us to replace the vector chromatic number with 4 times the clique number, giving a weaker version of our result. And finally, for our full result, we need to put even more constraints here. So that's all I have to say about the proof method. So let me finish by some open problems. So of course, EFGW conjecture and the Bollobás-Nikiforov conjecture are both wide open. So I will be very happy if there can be further progress made on them. There are 2 more open problems I want to mention. So the first one is a sort of conjectural Turan theorem for the positive square energy. So this is from Elphick and Wocjan's paper in 2018. and they conjecture this inequality, and then often wonder whether this is doable with the same technique. There's also a strengthening of the Bollobás-Nikiforov conjecture by Elphick-Farber-Goldberg-Wocjan in 2021. Oh, this conjecture says that we can not only sum over the first two eigenvalues, but the first omega eigenvalues, provided they're all positive. So of course, this is much harder than the Bollobás-Nikiforov conjecture, but I'm wondering that if we can aim for a lower, we can aim for a like slightly weaker bound, which provides a saving term that's on the same order as the predicted saving term. Okay. Yeah. Oh, yeah, these two are all like interesting conjectures, and wondering if the technique and I described is applicable to them at all. So that's all I have to say. So my main results can be found in these two papers on arXiv. And yeah, thank you so much for inviting me.
Okay, so thank you very much, Shengtong. Are there any questions?
It's Clive Elphick here. Perhaps I can just say thank you, Shengtong, for a very interesting and helpful discussion of the progress you've made. So well done and thank you.
Yes, thank you, Professor Elphick.
Well, I have the question. Yeah, you said that you think to prove the EFGW conjecture or the Bollobás-Nikiforov conjecture, you think that they are wide open, but do you think there is a good prospect of proving these conjectures, maybe pushing the techniques you have for both of them, for example?
Yeah, I haven't tried that for a while myself, actually. But yeah, I think there's still like crucial ingredients missing.
Mm-hmm.
That I just said. Yeah. So yeah, so I don't think it's like I don't think we're very close to either conjecture.